We cannot hear you. Oh, hello.
Hi,
Hello.
I found a fantastic paper from the group of Benakir, which I'll send you eventually. Just now I have to do something else, but I thought that we should generalize what it says to include spin-orbit interaction.
Okay.
I will send you the paper soon.
Who is the author?
It comes from Benakir, Carlo Benakir group.
Mhm.
How are you, Robert?
Fine. I mean, no big changes. Thanks to God, everything is fine. My mother is vaccinated fully,
Good.
and they promised to make vaccine for me starting with middle of February.
Which is good.
Yeah, it is. They will start.
Yeah. Very good.
So, and everybody is safe so far.
And how is Max?
I haven't heard.
Sorry for interruption.
Oh,
We are live on YouTube currently and about to start the seminar.
Okay,
so there will be discussion afterwards.
Yeah, but not this kind of discussion.
I mean, it can be this kind, but I suggest that we start with the seminar.
Okay, so I shut down.
Welcome everyone, welcome PCS members, welcome members of our advanced study group, and welcome our friends to this seminar. It is a pleasure today that we have Professor Leonid Gorelik to talk about his work. And I would like to invite our scientific host, Professor Robert Schechter, to introduce our speaker, please.
Thank you very much. It's my pleasure to do this job. Leonid Gorelik is our many years collaborator, more than 20 years. I'm happy to introduce him in this seminar. At this moment, he is member of our advanced study group. He entered this group a couple of years ago, and his work here is very successful, I think. He was graduated in Moscow Physical Technical Institute in Chernogolovka. It's a famous, one of the most famous physical institutes in Soviet Union, former Soviet Union, and known for keeping traditions founded by Landau. And in fact, Leonid was a student of Landau, direct pupil, direct student. So he is grandson, so to speak, of Landau. And it is really true in the spirit of what he is doing in physics, because what I could observe, it's the same tradition, the same approach to physics as we have traditionally learned from textbook of theoretical physics written by Landau and Lifshitz. It is implemented in his work, in everyday work. So his main scientific focus was on mesoscopics, different kind of mesoscopics, starting with research on property of metals in the magnetic field when magnetic field cannot be treated semi-classically. So beyond semi-classics, you will find that at some metals, magnetic field results in reconstruction of energy spectrum of electron, known as a magnetic breakdown. And a special type of such a breakdown, it's governed by quantum coherence of electronic waves. And Leonid was working with a person known for pioneering work in magnetic breakdown, Professor Slutskin in Kharkov, on this, and he defended thesis on this research and made a significant contribution in this field. In 1995, he moved to Sweden. And since that, we are collaborating with him closely. And mesoscopic, again, was a subject of our investigation. It includes quantum coherence and Coulomb correlations in metals. It includes mesoscopic superconductivity, weak links, and recently nanomechanics. In number of papers in prestigious journal was published on this subject, and most recently Leonid was focusing on nanomechanics in superconducting devices, when we can benefit from both quantum coherence of mechanics and quantum coherence of electrons and coupling of these 2 degrees of freedom. And today's presentation will be devoted to one particular subsection in this direction. So very welcome, Leonia.
Robert, thank you very much for introducing me, and you explained a lot of what I will present today. So the nanoelectromechanical phenomena induced by Josephson force. So of course, Josephson force, this is, we have immediate smell of superconductivity. And this, Robert mentioned, this is one of the line of researching in our group. And some results were presented by Dan Karadic in December, as I remember. And this is another result obtained in this direction. And this is everything is done with discussion and collaboration with people from Göteborg and Daejeon. This is a day parallel Park. But I want to say is that they are not responsible for today's presentation, because actually we don't have enough time and good opportunity to discuss everything, all details, because for obvious reason. And I think that this is online communication cannot substitute the real communication face-to-face near the blackboard and so on. So maybe I say something which they don't share with me. So they are not responsible. Okay, outline of this presentation. So first I will give some short presentation to the nanoelectromechanical system, namely what we mean when we say nanoelectromechanical system and which phenomena we would like to discuss. Then I will consider and explain the real system, which I will discuss. And then this system, this nanoelectromechanical system, consists of 2 subsystems, electronic subsystem and mechanical subsystem. And first I will discuss the property of electronic processes. And then after this appears Josephson force, how they induce and what can we treat as a Josephson force. Then I will discuss behavior of mechanical subsystem, which is actually main aim of presentation. And finally, I will discuss and demonstrate that this mechanical system under influence of electronic subsystem can demonstrate different behavior. It may be cooling of this mechanical subsystem or some excitation of the self-sustained oscillation in this system, and then conclusion. So let's start from the beginning, nanoelectromechanical system where we are. So what we consider as nanoelectromechanical.
I don't see your presentation. I see your picture, your photo. Is everybody, do you have?
Yes, I can see. Perhaps you can try if there is in the lower corner, maybe lower right corner or on the side, if there is a small screen with presentation. If you click there, it will open the presentation on big screen, and
I cannot exit. There is exit full screen. Is it this? No.
Perhaps you can try this.
What?
Danka, can you see my presentation?
Now I can see.
Mhm.
Yes.
Okay.
Let me
Okay.
see. No, but no, I cannot see.
You should look for view options or for view on the top of your screen.
View options, yes.
Touch that.
Side-by-side mode, this is.
Yes.
Okay, and then how to make it big? Aha, okay. Okay. And now I can see, yes, thank you. Sorry.
Okay, this is a typical nanoelectromechanical system. It consists of two bulk reservoirs, which are under the bias voltage, and they are not in equilibrium. But they are connected through some mesoscopic object. It might be quantum dot, a nanowire, what else. And then the electronic transfer through this mesoscopic link give rise. And this microscopic link has some mechanical degree of freedom. Yes, and there is a power exchange between this is working body, so to say, and this is mechanical subsystem. We will consider usually the simplest situation, most quantum situation, when the working body is represented by single electronic level. Actually, double generic with respect to spin. This is simplest what we can suggest. And mechanical system is presented by mechanical harmonic oscillator. So this is also simplest mechanics. What is the characteristic of this oscillator? This is amplitude of 0-point fluctuation, which actually of the order for typical system, nanomechanical system of the order of picometers. And this is a Hamiltonian which we will use. And this Hamiltonian is written for normalized on this amplitude of 0-point fluctuation. 0-point fluctuation. So this is the general mechanical system. What performance can we expect? So mechanics may be described classically or from quantum mechanical point of view. If we consider mechanical element as a classical element, there are two options. If we get the power from this working body to this mechanical element, so we excite some dynamics of oscillator, and then it should be something like a limiting cycle in the phase space, because a stable situation when we have zero amplitude of oscillation, impossible. We put power inside. But when we have vice versa situation, we have some power flow from mechanical system to the electronic subsystem. So of course it will be some damping of the mechanical subsystem, and we will have some stable point on the phase space. If we now take into account some stochastic or quantum fluctuation, of course we cannot now describe oscillator using only momentum and position coordinate. We have to introduce this probability distribution. So we describe our oscillator with probability to find oscillator at point X with momentum P. This is the probability. And then in first case, what is this? We will have, instead of this limiting cycle, some smeared limiting cycle, some distribution function, which has maxima in the vicinity of this limiting cycle. But another situation in this case, when we have some power which we take from mechanical subsystem. In this case, this is, of course, we smear this point around P and X, and we can expect, for example, if we don't have any oscillations, that the energy, average energy which we calculate will be defined by temperature if we connect it to the thermal reservoir. But in our case, when we connect to the non-equilibrium subsystem, which is not in equilibrium but not equilibrium, we have two possibilities. Maybe the average energy will be greater than the temperature, and in this case we can speak about the heating, but it might be also smaller, much smaller than external temperature. And in this case, we will speak about cooling of the mechanical system. And this is most interesting regime of behavior of mechanical system in nanoelectromechanical situation. Of course, from these three, it's most interesting this one, and we will focus on this situation. Some history. The first, this is instability and then pumping regime was predicted in this work many years ago. And this is some Coulomb dot which are moving between two reservoir and voltage applied between the reservoir induce some electrical field. And then we can have some charge transfer between two reservoirs. Then later it was shown that it's more realistic system when we have carbon nanotube suspended between two leads and attached to the STM electrode. So this is the flow from STM to nanotube and then to the leads. It was shown that it's possible to observe cooling of the mechanical subsystem, and this is actually bending vibration is presents the mechanical subsystem. Also, in both these situations, the force acting on the mechanics was induced by electrostatic phenomena. So it means if there is a charge on nanotube, there is a force. If no force, because there is some electrical field presented. But it turns out that it's possible also to realize this force not using electrostatic, but using some magnetic properties, using exchange interaction, and this was done later. What is actually most ingredient of all these phenomena? First of all, what is very important is that the force acting on the nanotube induced by electronic dynamics depends on the population of the either Cooper pair box or nanotube, or maybe this object. And at its turn, the population is controlled by the rate of exchange between the leads and working body. So if we change the position, we change the population changes the force changes the position, and so on. So interplay between all these two properties give rise all these phenomena which I described before. And then natural question appear, can we have something interesting if we don't have this condition? We don't have force which depends on the population of the working body, and if we don't have the dependence of exchange rate between working body and reservoirs depending on position of the mechanical subsystem. Okay, then this next system under consideration, the system which we want to discuss. Of course, as a theoretician, I can present you simply Hamiltonian and that's it, but I prefer to have something realistic in mind. So what will we consider? So carbon nanotube, which we can treat at a single level quantum dot. it's possible if we have finite length of the nanotube due to strong space quantization inside nanotube. Suspended above the range of normal electrode. Yes, and connected via tunnel contact. And then above the nanotube, we have superconducting STM, which is superconducting state. Then we bend nanotube back and forth towards the STM. We increase the tunneling coupling between superconducting STM and quantum dot. If we go in this direction, we decrease this coupling. So this is some type of coupling between mechanics and electronics. Then we have applied voltage to the normal electrode, and superconducting STM should be at grounded and have zero bias voltage. Now, Hamiltonian, of course, consists of 4 terms. First one, this is Hamiltonian, which describes electron reservoir. So this is a standard Hamiltonian. We add also the voltage, which shows that this is voltage shift the Fermi distribution function with respect to Fermi level in the superconductor. Another term, superconducting term, this is also standard electron term, where we include also superconducting order parameter with this is non-diagonal elements. This is quantum dot. This is a single level quantum dot which describes the population of this energy of this level, and this is a population. There are 2 possible states. It's electron with spin up and electron with spin down. It's the dot. And also this quantum dot contains the mechanical degree of freedom, which describes this bending oscillation toward and superconducting STM.
Professor Gorelik, we have a question from Professor Entin Volman.
May I ask now?
Yeah, please.
Don't you have to include the voltage in the superconducting Hamiltonian?
No, the superconducting electrode is grounded.
So the voltage does not affect the superconducting phase?
No.
Okay.
There's only one superconductor, there is no phase at all.
So there is no effect of the voltage on the superconductor?
The voltage affects superconductor, yes, if we have Josephson junction, some coupling between 2 superconductors, and then the voltage drop between superconductors affects the phase difference.
Yeah, but
this is only one superconductor.
Yeah, but maybe you have proximity. Can't you have proximity effect?
But then you have the voltage drop between the nanotube and superconductor. No, of course, you can imagine some proximity effect from superconductor to the normal electrode, but I don't know. This is something.
Thank you.
Yeah. So there is no voltage, no IC Josephson effect, and no Josephson effect at all. Okay, so this is the Hamiltonian and the system. And what will we do with this Hamiltonian? No, I cannot. So, of course, we will describe the state of our system using Liouville equation. And even more, we will look for the stationary solution of the Liouville equation. Because we believe that to observe transition process is very difficult. But if we take our system, apply the constant voltage, and then after some time, very short actually time, we will come to some stationary regime which doesn't depend on the initial condition. And the feature of these stationary regimes will be in the focus of our consideration. So then the mathematical tool and our approach, how will we consider this? I am sorry, I have, can you see the title of the slide?
Yes. Reduce density
because
matrix.
there is something I cannot see in my okay, but I know. Okay, so this is reduced density matrix representation. So we will consider the stationary regime when derivative equal to 0, and we can rewrite this equation in such way, dividing this is total Hamiltonian in two parts. This is the zero Hamiltonian which describe our system, and then we eliminate tunnel Hamiltonian. Then from this, instead of this equation, we can jump to this equation. This equation is absolutely similar to this equation, but what is important then we eliminate and take square of the tunnel element here. Actually, we resolve this equation with respect to this side and then substitute back. So this and this is a result substitution. This is absolutely two equivalent equation. But now what we can do? We have very small mesoscopic object and we have two macroscopic leads. So we can imagine that state of our mesoscopic object very little affects the state of the lead, but not vice versa. So we will suppose, and this reduced density matrix approximation, that the total matrix is a product of tensor product of three matrices. One of these is density matrix, reduced density matrix, which describe quantum dot with mechanics. And actually, this is a total density matrix where normal and superconducting eliminate. At the same time, this is two states. Density matrix which describes the state of superconductor lead and normal lead is taken as like they are in thermal equilibrium. What is the reason of this and what is the limit of this representation? We believe that actually interaction between lead and mesoscopic subsystem, in the leads, relaxation is very fast, and then it's faster than any processes which couple electronic mesoscopic system with leads. So all times this leads in equilibrium. So this is reduced density matrix approximation, which we will use and usually we use in our consideration of mechanical process. Where is this okay. Next, of course, what we will do, we want to substitute this ansatz into this equation and take trace over superconductor and normal lead and eliminate and get only equation for the reduced density matrix. We can do this, but it's much easier to do this if we have some restriction. First of all, we suppose that the superconducting gap in superconductor is biggest parameter. So we don't want to consider some quasi-particle spectrum in superconductor. Then we suppose that the voltage also is quite big, but smaller than the superconducting gap. It's greater than the temperature, that frequency, the Poisson level position, and gamma is the rate of exchange with normal lead. Is also smaller than the voltage. This assumption is quite realistic from my point of view, but allows significantly simplified all mathematical derivations. So what we do after we eliminate this is leads, we get the following equation for the reduced density matrix. So this is, of course, the Hamiltonian which describe quantum dot, and this is two terms, and this is Hamiltonians now consist of level and mechanical part. These guys come from superconductor. And this is, it's true that there is appears something proximity induced order parameter inside nanotube. Inside this is quantum dot. Now you can see that appears some non-diagonal in electron presentation terms, very similar to the one which we have in superconductor. This is proximity effect. But proximity effect on from superconductor to nanotube. And what we have here, this is comes from the when we eliminate normal metal. Normal metal has continuous spectrum, no gap, a lot of quasi-particles, and these guys give some Lindblad term in equation. It's two different Lindblad terms. And what they describe? Actually, they describe exchange between normal lead and quantum dot. We take big voltage, so this term which we will consider shows that if voltage greater than 0, so chemical potential much higher than the position of electronic level, there is possibility only that electron tunnel from reservoir for normal electrode to the dot, if corresponding place is empty, but not vice versa, because all due to the Fermi distribution and Pauli excluding principle, all places are forbidden. So this describes that only processes of tunneling from electron to the dot is possible, not vice versa. But if voltage is smaller than 0, so corresponding place is empty, and then it's vice versa situation. There is no possibility to tunnel from normal electrode to the dot because there is no such electrons at all. The places to Fermi level is too low. At the same time, it's possible immediately from tunnel from the dot to the normal. So this is two different possibilities.
Leonid, may I ask a question?
Please.
You have this in front of Lindblad term in this equation, which is marked gamma. It means that you sort of derive this term. The same time, Lindblad term is phenomenological treatment. What is how you get this term? I mean, is it a combination of phenomenological Lindblad term and then derivation using tunnel Hamiltonian, or how you got it?
Okay, actually, usually Lindblad term you introduce in your system, yeah, phenomenologically, yeah. But actually, this Lindblad term describes the real processes. And if you want to specify and to consider the real processes, you will get this very special Lindblad term.
So how you got it? I mean, you just
I just substitute this ansatz to this equation, then trace over normal electrons, and then I get this. Actually, I get this. That is Lindblad. I call it later. Because it's actually what I obtain. This is Lindblad term with a special situation, nothing more. Because it's not the most general form of Lindblad term. If you have coupling to some another system, so you have more general form of Lindblad, this super operator. But in this very case, this is Lindblad operator can be presented like.
So you started with a general Liouville equation, which for whole system, you introduce Lindblad term in this equation?
No, no. Again.
So let me see. I understand it like this. You introduce Lindblad term first.
Okay, Robert.
Let me finish. You introduce Lindblad term in the Liouville equation general, and then trace this equation with Lindblad term over states in the lead.
Okay. Okay, look, let's forget about the Lindblad term. Let's forget. No Lindblad term. I start from this, substitute this, and I get this.
Yeah.
Yeah. How you call this? If you want to call Lindblad or not, it doesn't matter.
So you didn't introduce any Lindblad term?
No, absolutely.
I see. It's just you call it now.
Yeah,
so you derive this term microscopically, so to speak.
Yes.
It's not phenomenological. It's
no. Okay, guys. Sorry. Okay, let's go further. The electronic processes and Josephson force. So let's consider the situation when we eliminate the motion of carbon nanotube. So exclude mechanical degree of freedom, any dynamics. So now position we can treat as a classical variables and the parameter of the system. Oh. I'm sorry. And in this case, we have the following equation. For the reduced density matrix, no mechanical degree of freedom is only parameter, whereas this Hamiltonian, you can see that the standard Hamiltonian of quantum dot with proximity of parameter. Now it's possible this one, and this is Lindblad. This, okay, don't Lindblad. Okay, this is operator L. If you
tunnel source.
Yes, tunneling source, which describes the exchange. And we will consider actually the two possibilities, but we will consider the only one possibility. This is when voltage is greater than zero. And it's very important property of this equation that actually if we change the direction of voltage, so we change this term to this term and simultaneously change the sign of epsilon here, we will get the same Hamiltonian as the same equation. So our system is symmetric with respect to change of sign of energy level below or up under the Fermi level and simultaneous change of the bias voltage. Okay, then this is actually quantum level, and there are four states, four natural electronic states on this level. First one is a state which describes the empty dot. This D0 equal to 0. Then another state which describes the double occupied dot. So the dot where we have electron with spin up and electron with spin down. Then the state we have single occupied with spin up and single occupied dot with spin down. So naturally we have four states. And this is the fourth state. And all these terms as, I'm sorry, Lindblad and Hamiltonian describes the transition between states. First, if we have empty dot, what is the possibility? It can disappear. Why? One electron can tunnel from normal lead, for example, the spin down, and then we have transition from empty dot to the electron occupied with spin down. Or we have some electron with spin up, and we have this guy. But if we have zero electron, it's possible that two electrons, namely Cooper pair, tunnel to the quantum dot from superconductor. This is good. And then we have transition 0, and then we have 2, it disappears. Then if we have one electron, so it cannot jump back to the normal reservoir because all states in normal reservoir are occupied. But it's possible that another electron jump to the dot, and then we have double occupied state. Of course, we can move in this direction. What can happen with double occupied state? It's possible that these Cooper pairs, two electrons, disappear in superconductor, and we have transition from double occupied state to zero occupied state. So all these processes, this is processes with gamma, are described by this Sorelin Blatt operator. And this process and have some stochastic nature. And this process exchange transition between 0 and 2 electrons is responsible for the coupling to the superconductor. Okay, so to describe this, we can introduce this as matrix. So we have 4 states. So the space of Hilbert is 4. The dimension of Hilbert space is 4. And then density matrix is, this is 4 by 4 matrix, which contains 16 elements. But we are lucky we can immediately say something and reduce significantly description. First of all, these blocks, which describes some superposition between state with integer and 1/2 spin. It should be equal to 0 due to super selection rules. It's possible to have some superposition of electron with odd and 1/2 spin. Yeah. Then actually these elements, non-diagonal elements here, which have some superposition between state with single electron state with different directional spin, also equal to 0, because otherwise we will have some spin directed in some direction, but we don't have this direction. So we can reduce this density matrix to this one, and then we immediately can say that population to have the probability to have the spin up equal to probability to have spin down, because there is no any difference between spin up and spin down, and it's symmetric. So we have, instead of all this, then Hamiltonian. Hamiltonian consists of, this is electronic part, which describes the exchange, and then this is the electronic state of single occupied level. And then we can present it in such way, eliminate this diagonal part. So, and this diagonal part immediately disappear because of its commutes with everything. And then we have only so-called Cooper pair Hamiltonian, which described by this angle. And then finally, we have representation for Leonid Blatt operator. Now we have 1, 2, 3, and 4, 5, this is complex number variables. But what we can do, first of all, it's convenient to use, instead of row 1, this is another one. Variables is linear superposition, so we will, instead of row 1, we will use the sum. Then instead of this 1, 2, 3, 4, it's convenient to use this representation to present this is as a diagonal matrix, and this is Pauli matrices. And this is now, this is some vector which we present in such way. Okay, boy. Okay, doing so, we get this number of equation. We are lucky that actually this equation is trivial, because the total probability should be equal to 0. And then we have very simple equation for this guy, which is equal simply 1/2. But then what's important, we have some equation for this guy. What is the behavior? What is the Cooper pair state of one quantum dot? And this is described by this equation. It's easy to solve this equation. This is M is 3 by 3 matrix. Actually, we can see here. And then solving this equation, we can calculate, for example, current. The current is equal by this formula, but now I want to spend some time and to analyze what is the electronic process responsible for the charge transfer. So we have normal lead, and superconductor condensate, and suppose that initially we have one electron on the quantum dot. This electron cannot jump here because everything is filled, and it cannot jump to superconductors because the quasi-particle level is too high. But what can happen then, one electron, another with spin down can enter this and create, in some sense, Cooper pair. And then this Cooper pair can enter superconductor, but it's not the eigenstate of system. So we will observe some quantum oscillation back and forth from superconductor to quantum dot and vice versa. But at some moment when it's empty, another electron can tunnel here. And then this Cooper pair will be blocked. It cannot now tunnel and then disappear. And this results that two electrons appears on superconductor, and then another electron can jump, again oscillation, and so on and so on. This is the current. But what about Josephson force? We can calculate now the average energy stored inside this electronic subsystem. We calculate this energy, and we can see that this energy depends, of course, position of the level, and also non-diagonal element which characterize the superposition on zero and double occupied dot. Then what can we see? Okay, this is energy depends on a position. So let's take the derivative and say that this is a force. Okay, and this is actually what we can treat as a Josephson force. And then it's very tempting. Okay, say, okay, we have force which depends on X. Now let's substitute this force in the Newton equation, get some dynamics and so on. But this is the average force, actually. This is the average force, I'm sorry. But what is average? The average, this is Hamiltonian. It has two eigenvalues. This is actually Andreev levels. And then when we measure the energy, we get either one result or another, and then reduced of density of wave packet. Then if we wait some time, we again measure the energy and get either one energy or another. Again, reduce packet, then again wait some time, again make the measurement, and then when we take the average, then we get this result. But then the question is, who makes these measurements? Nanotube? Who takes this trace? Is it nanotube? This is strange. When I start to think about this, we immediately come to the problem of the quantum measurements, then to the problem of collapse of electronic packet, then inevitably we come to the question, do we exist, and so on. And then Feynman said that he thinks that nobody understands quantum mechanics, and then it's not clear what to do. But then there is another help comes from the Schopenhauer interpretation of quantum mechanics. So it means that we have to start calculation and don't stop to think about something which is not.
May I ask you a question?
Yes.
You see, I understand the general thing. It's difficult to understand in quantum mechanics who make an average. Here we have actually open system. We have three bulk bodies. I mean, two superconductors, or one superconductor and two bodies. We have two bodies, normal and superconductor. And we have tunnel Hamiltonian. Now, if we bias this system, we introduce that there is a flux of electron incidenting on our device from the normal electrode. And electrons are coming one after another because there is a current in the system. If electron left normal lead and goes to superconducting, then there is a hole in a normal metal. This hole relaxed, and electron is taken from infinity on normal metal to repair this hole. And then next event happened, and another electron tunnel. So we have this sequence of tunnelings of electron, one after another, to our device. And average could be actually average in time. We really measure current during certain period of time when number of electrons coming back and forth, and we have sequence of quantum experiments. One observe two-level system in upper level. One event consider two-level system in another. So we have this really statistical performance in our system. And average is statistical average.
Average of what?
Average of current. We measure.
Yeah. Okay, so what?
So I think that if we are interested in properties of this device, average in time, it will be statistical average.
Okay.
So there is no.
Yes.
No.
I agree with you when you speak. I agree with you. I agree with you. I agree with you when we speak about the current. Okay, but what is the question? I speak about the force. I speak about the energy.
Okay, one can consider, for example, average displacement of the system during this microscopical. You have microscopical time of electronic tunnel through the system, and you average displacement over such a short period of time of many events.
No.
So whatever physical property you consider, you can average this over fast microscopical tunneling events.
Okay, look, Robert, we can discuss this later, but I
just want
I am on a Feynman position.
No, it's not the same. We don't have single measurement here.
Yes, but look.
We have the flux of electrons. We have a really statistical system. It's a many degrees of freedom.
Okay, I don't agree, but okay, let's.
Okay, okay, sorry, but it's similar.
No, okay, but I have. Oh, so what we have to do? So we have jump to mechanical subsystem and to consider the basic equation. So we have to come back and to re-enter the mechanical subsystem in our Hamiltonian, because this is no question how to describe the interaction with in quantum level. So now we have the same Hamiltonian, but we add this mechanical subsystem to electronic subsystem. But what we have to change, also we have to change the density matrix. Now we add the mechanical subsystem, and Hilbert space of our dot is now a tensor product of this is wave function of mechanical wave function to the all this Hilbert space with this described fourth state of the electronic subsystem. This is a density matrix. Of course, it has the same form, but now instead of the number, this is density matrix and X representation. This is now quantum density matrix. And it's more convenient in use not X and X prime, but another X and momentum. So to use a Wigner representation. Yes, because if we want to calculate some quantum mechanical averages, so we can consider in some, very often we can treat this Wigner function as a distribution function and simply take the integral. We want to consider some average position, integrate with this function with respect to X or average momentum, to multiply by P, multiplied and so. So this is very convenient object. Then we can rewrite the equation, and this is the main equation which we use. And you write in this form. So you can see the some modifications. This is the first equation. Before it was trivial. This is the double W sigma, it was before equal to 1. It doesn't depend on the position, but now this is some function of the position and momentum, yes? And this is actually the function which describes the behavior of mechanical subsystem. It will be in the focus of our consideration. So we have add this equation. Then, of course, we add this from mechanical Hamiltonian. Let's specify what is L. This is, okay. And this guy, before, okay, this is red one, which appears due to our description of mechanical subsystem. If we take away this red one part, we come back to this situation which we considered before, where mechanical degree of freedom was frozen. So this is equation. And then, of course, we can boundary condition. We cannot consider a very big deviation of Bayesian deviation. It should be smaller, at least as the distance to the STM tip. Otherwise, it will stuck the STM, and all our consideration is not valid. Okay, now bad news. We have 1, 2, 3, 4, 5 equations. Yes, and bad news is 5 equations with coefficients which depend on x. And good news is actually this is linear equation. I think this is a typical equation for the in the field of in electrodynamics, which considers this is artificial system, and this also solves this linear equation for different variables, but for electrical and magnetic field. And but actually, I'm not specialist, and then okay, this is another joke. So to analyze this equation, we need actually small parameter, and we will use a small parameter. One small parameter exists. This is epsilon. It's a ratio between the amplitude of zero fluctuation and tunneling legs. One. Yes, but it's not enough. It's also, we need some small parameter that this epsilon multiplied by delta, which characterized like this. You see, this gives weak coupling, because if all this epsilon part equal to 0, so we don't have any coupling between electronic and mechanical subsystem. So, and then we also have a lot of parameters, and we can use relation between these parameters to develop different perturbation scheme for solving these 5 equations in partial derivative. Okay, what we will consider, adiabatic limit is quite natural. This omega is quite small, less than gamma. We can eliminate all 4 extra variables and get the equation for the interesting value. So this is a distribution Wigner function for the mechanical subsystem. So it has such form, and I want to discuss this. First of all, this guy describes simply some effective force, maybe which induced by our interaction between electronic and mechanical subsystem, as really can be treated by Josephson force. This guy describes some effective friction, which due to the exchange of power between mechanical electronic subsystem. And this term describes some diffusion induced by stochastic and quantum fluctuation. Unfortunately, of course, this is expression for this coefficients. You can see that it contains some inverse matrix 3 by 3, and this is even more complicated, but it's possible to calculate. But the expression, you can believe me, looks absolutely ugly, so I don't want to present even. Also, what we add here to interaction with thermodynamic environment. Again, this is interaction induced by interaction with non-equilibrium electronic subsystem. And this is what we get new. But we have some also thermodynamic environment. It might be some surface phonons and so on, which acts only on the mechanical degree of freedom. Of course, if this interaction coefficient equal to 0, so we have only interaction with the environment, and then we will get the Wigner function which characterizes the thermodynamic distribution. Okay, and this is quality factor, so which is usually for system which we consider is 10 to the 4 to 10 to the 16. This is 1, and beta is some coefficient which depend on temperature. It may be 0 temperature, so we come to the ground state. And if the temperature is not equal, so we have something different. To analyze this equation, it's convenient to use that epsilon square is of the order of 10 minus 4, and Q is also in the order of 10 minus 4. So this is two guys is quite small. So it's quite natural to develop perturbation theory with respect of these two parameters and take a zero approximation that they're equal to 0, and then to look for the sum correction. It's convenient to do this in angle action representation. So we'll look for the Wigner function in action angle representation in such form. So when epsilon equal to 0 and Q equal to 0, so we have some Wigner function which depends on the on amplitude, and then we have some small correction to this Wigner function. So what we want to know, but we don't know, this may be any function of amplitude satisfies this equation when epsilon equal to 0. So we have to find which function. And then it's possible to get equation for this function development perturbation theory. And now it looks much better. This is very simple differential equation with respect to A. Yes, this is series plus. And we can solve this differential equation and find what is a function distribution function. I have no. So now cooling and excitation of self-sustained oscillation. So first, let's consider the case of small amplitudes, when amplitude of this behavior property of this Wigner function and small amplitude. So if so, we can take this coefficient at 0 amplitude, and then immediately solve this equation. And to get that this is equation, solution is have this standard form, and then we will treat this better as an effective inverse temperature. This is simply solution. So if beta is greater than 0, so we have this Wigner function decay with amplitude, so probability to find system at 0 amplitude has a maximum, and decay with increasing amplitude. But if beta is smaller than 0, then probability to find system at 0 amplitude equal to 0, and probability to find system with increase with amplitude. And then we can say that this manifestation of the fact that now the state, static state is not stable, static state which correspond to x equal to 0, p equal to 0. Okay, next. Then we, of course, this is beta, which is presented as very important. First of all, let's neglect with this thermodynamic. Let's suppose that the Q factor is 2 to very, very big, and what comes from only electronic subsystem. From electronic subsystem, we have the following expression for the beta. And what is important? The sign of the beta depends on the sign of epsilon. It depends on the position of the electronic level inside the dot with respect to the Fermi level in superconductor.
So you use the same letter to introduce epsilon position of the level in small parameter epsilon.
No, okay, I am sorry. Yes, it's my mistake. But actually, if you look, this is a different epsilon. If you look carefully, you can see that this epsilon and this epsilon is different. As I don't correct. Okay, sorry. Okay, this is important. But then the sign of beta also depends on, this is some function which depends on the ratio between gamma and delta. And if we make some calculation, it turns out that if gamma is much greater than delta, this is negative, yes, and so beta is negative and we have excitation, and if gamma is smaller than delta E, it's positive. So we have, let's say, cooling. Okay, let's first consider cooling situation. This is very important. This, as I mentioned, the system is invariant under replacement. So if we want to change the sign of epsilon, we have to simply to change the direction of the voltage of the bias voltage, and that's it. So if we have the fixed system and we change the direction of bias voltage, we simply jump from this situation to this situation or vice versa. If we have this situation changing bias voltage, we jump to this situation. Okay, then calculation which can give you the beta. Beta is, this is a red is excitation, blue is cooling, and this is the real dependence on beta on epsilon and gamma respect to delta. And you can see that if epsilon equal to 0, we don't have either cooling nor excitation. We have completely influence on the thermal path. So this is, if we take this cross section, we will get that, okay, this effective beta equal to 0, as I mentioned, at epsilon equal to 0, but then it starts to decrease. So the excitation process increase, and then at big amplitude it's also decrease. This is excitation, but what we can say in this region that only the ground state, because this is oscillator is unstable. But if we have if we take the cross section somewhere here, we will get some cooling situation, and then the cooling situation looks like this. So beta now is positive. This is contribution to at 0 epsilon. This epsilon position of the level equal to 0, but when we change epsilon, there appears some maximum value. So it corresponds that the maximum inverse temperature appears, and then the indices what is possible inverse temperature, which effective inverse temperature we can achieve. Then it's two regimes. When omega is much less than gamma, the maximum possible inverse temperature is omega divided by gamma. But if we approaches gamma to the omega, it may be of the order of 1. But if omega is greater than gamma, it turns out that maximum, beta maximum equal to 1, and this is correspond to ground state cooling. It means that the Wigner function in this case corresponds to the Wigner function of oscillator ground state, and it's possible to achieve this when we have the special choice of the parameters, other parameters. Okay, this is about cooling.
Leonid, one moment, just to understand what is the role of superconductivity. You call it Josephson force and effect of all this on all this phenomena superconductivity. It's difficult to guess, I mean, how it qualitatively influences, but what I can see that if delta goes to infinity, it means that in your graph, down graph, I mean, you're going to beginning of the coordinate. So your beta goes to 0. If delta goes to infinity, your beta goes to 0. Beta is inverse temperature. So you have infinite temperature on the dot if you infinite temperature of the vibrations if you have very, very big gap. How we could understand this?
Again, please.
So if you look at your slide here, to the right, down figure, I mean, with the maximum, the down. There are two graphs here to the right,
Yeah.
upper and down. I would look down. If delta goes to infinity, argument goes to 0.
Actually not.
No, but I can see in the graph, I mean.
You can see that it's decay, but I can tell you that actually it will saturate to some value.
Okay, what value it is?
I don't know. This is numerical simulation.
Well, okay, tendency is that temperature of mechanical vibration increase.
Because this is cooling. First of all, this is the cooling regime. This is first one. Yeah. Then we obtained when we neglect interaction with the thermodynamic environment and so on.
Effective temperature, beta. If beta is very small.
No, this is a big temperature, a big fluctuation.
Could we understand why this fluctuation become very big if gap become super?
No, for example, look, if you have only diffusion, for example, consider you have random force which acts on your oscillator, and you don't have damping. You have some diffusion. For example,
why we have diffusion? You see, I physically ask the question. I would like to see how superconductivity affects heating or cooling qualitatively. And I take a limiting case when superconductivity is very strong, a gap is very strong, Josephson coupling is very strong. Now, we have big fluctuation of mechanical vibrations, quantum fluctuations, very big. How we understand that if superconductivity is very strong, we have a big mechanical fluctuations. I would guess that superconductivity is a system with a 0 temperature.
Look, if you want, of course, it's not correct picture, but maybe it fit to you. Actually, the situation looks like this, that we can consider that Cooper pair jump from superconductor to nanotube, from superconductor to nanotube, jumping from nanotube, it generates some force, and in one direction and then in another direction. Yes, and then this force is proportional to the delta. Mm-hmm. And then if delta is very big, this is fluctuation of the force approximately with Rabi frequency of Andreev oscillation. Yes, but of very big force. And then it will give some diffusion on your mechanical subsystem. And of course, this is diffusion coefficient will increase when we increase this is in force. Well, that's it. Mm-hmm. It's shaped back and forth, back and forth, back and forth, back and forth, but with very big amplitude if you want.
Not back and forth, but it's important that normal electron are coming and you interrupt.
No. If delta is much greater, yeah, then it's no way to come to a normal electron. The all force take place during this period when we have when there is normal electron, there is no any force. Okay, I have out of time. Can we discuss it after?
Okay, sorry. We'll discuss it later.
Okay, final. Then what's happened when we consider excitation regime? Now we have to take into account that really this coefficient, especially friction coefficient, and unfortunately this is a diffusion coefficient, which Robert would like to discuss, increase with amplitude. Yeah, and it depends on amplitude. And what is this pumping and diffusion? And then what's happened when this is epsilon A, it's big deviation from equilibrium position. So we can see that this derivative of Wigner function equal to 0 when this coefficient equal to 0. So it means that this Wigner function has maximum at this value. Of course, it's impossible when this is gamma A only positive. Yeah, so it cannot be equal to 0. But fortunately, this is coefficient decay with increasing of amplitude. So even if at 0 amplitude it is negative, yes, and induce some pumping process. At big amplitude, this real Q factor, thermodynamic Q factor, will overcome this one and saturate this is oscillation which we can generate. Okay, we make some calculation at given parameters and obtain the following structure for the Wigner function as function of A. At small gamma, when this is a positive, so we can see that simply we have some cooling regime which correspond to this one. But at big gamma, when this guy is at 0 is negative and overcome this quality factor. So at small amplitude, we have pumping, then we have increased some maximum of Wigner function, and then again at big amplitude, we have decay. And then this is actually correspond to this picture. And then this is correspond to what we have the excitation. Of course, again, everything depends on direction of bias voltage. All this picture we obtain a positive direction of bias voltage, but now if we change the direction of bias voltage, we can jump from this regime to this regime, or from this regime to this regime. So keeping the system as the same parameter and changing of bias voltage, we can get either, depending of bias voltage, we can get either self-sustained excitation regime or cooling regime. Okay, I use all my time. And this is a conclusion. Okay, thank you for the attention. That's it.
Okay.
Thank you, Professor
Questions?
Gorelik.
Just to have conclusion, if we would like to draw very general conclusion from all this analysis, what we can say, what superconductivity do with mechanical vibrations? Is there any distinct feature which we can observe, or it's just a complicated phenomenon with many parameters, many regimes? Is any could we say that superconducting gap affect nanomechanics significantly due to, or we cannot draw such a conclusion after that?
I cannot, I don't understand, I cannot say so. So we have nanomechanics, we have the typical processes. Can you give me some example that you can say that something is absolutely new and bring something? No. You have current in this case, in this case, in this case. Can you say that this is new and you never have such behavior of IV curve, for example?
You answer my questions to my question.
No, but yes, of course.
I cannot, and that's it. Or maybe in some cases you do. What basically, we don't have any effect of phase coherence here in this system.
No.
We just have another type of charge transfer. Electron cannot by itself go to superconductor. Only if two electrons are accumulated, then it affects kinetics of charge exchange. Electron can from normal lead go by one by one, but to superconducting only by pairs. So on, all these jumps are incoherent. Cooper pair jumps are incoherent, and single electron incoherent. So we have exchange by pairs with superconductor and by electrons with normal metal. And we are interested how mechanics, vibration of mechanics will be affected, taking into account new force, of course. That's probably the only special here is a special force, because otherwise no phase coherence here, I mean, so to speak, involved in this system. What force give us just
look
coefficient?
I mean, look, first this is what is new for me. The typical, of course, we have performance of mechanical subsystem. And this is this slide. This is all possible scenario. What else can you imagine? Of course, more complicated, it's possible. For example, we have bistable situation. Yes, it's possible. It's not presented here. But what else? What can you ask also about the mechanical subsystem? I don't know.
My motivation, Leonid, was simply like this.
Listen to me. Listen to me, please. So this is the answer we get. This is what we can expect, or what we ask for. Yeah. Then about system. The next situation is that typically we have this condition that force. By the way, what is force? Force doesn't exist in quantum mechanics at all. Force appears in first three Newton law. First one, second one. There is no analogies of force in quantum physics at all. Of course, you can call something like force, but it's absolute classical logic. Nevertheless, this is we have classical description, and we can say that some force, if you want, depends on the population of the gray. It's typically. And then this population is controlled by displacement. In this situation, is tunnel exchange rate with normal electrodes. We don't have either one nor another in our system. Nevertheless, we still to have all these phenomena. What is my point of consideration, my result? Of course, it's not something new direction in physics and some big discovery.
I was thinking of a pragmatical point of view. Suppose that you have mechanical machine working, your vibration and so on. And I want to affect this mechanic in certain way. And I say, oh, superconducting would be good for this. If we bring this mechanic in contact with superconductor, we will change this mechanic in desirable way. Is there any conclusion that superconductivity makes this mechanic behave differently in a certain distinct way?
Sorry, the question is, differently with compared with what?
With absence of superconductor.
Okay. I can tell you, if here in this system, you increase the temperature and go below the superconducting transition, so we have two normal electrons, you don't have either pumping nor cooling. You will have only heating. That's it.
If we neglect Coulomb force, of course.
Yes, of course, we neglect Coulomb force. Of course. If we below superconductivity, we don't have any significant mechanical performance. Now we decrease the temperature, go to the superconducting regime, and then we get possibility to control mechanics, and very dramatically control. Depending on voltage, we can either cool down at almost ground state, either excite up to, excite to this is self-sustained oscillation, depending on bias voltage. So if it's okay for you, that's it. But I can tell you that maybe another mechanical system based on another principle exists, which also allow to do something like to get the same phenomenon. Who knows? I cannot be responsible for everything and to compare with everything to say that this is very special.
So you have paradoxal thing. If you let one of the electron be superconductor with a zero temperature, so to speak, I mean, with a big gap, we may heat our system actually.
Heat mechanical system.
Heat mechanical system by attaching cold superconductor to this system.
Okay, if you want.
That's interesting. Yes, that's interesting. Okay, thank you.
Do we have any further questions or comments?
I wanted to ask about the scale of Coulomb interactions, the Coulomb blockade scale comparing to other parameters, because it's not been taken into account here.
Look,
question.
Actually, it's here. No. Yeah, it's here. So you see, I have two occupation of two level. Yes, it's less than delta, less than voltage. I can add here Coulomb blockade. For me, important that external voltage allow jump on the dot another electron, even this electron already, one electron state already occupied.
So it's much smaller than that. It's much smaller than all parameters here.
No. It should be smaller only than this.
Voltage and delta.
Yeah. We have simply to add this Coulomb interaction to this term, and that's it.
Leonid, to this question, what Danke said about electrostatic force. Of course, this force will, if you apply voltage to the system, you get electric force in your device.
No.
But you apply voltage between normal electrode and your wire. There is this voltage create in a space electric field. Now the question is, to neglect this electric force on your system, you need voltage smaller enough than your Josephson force and so on. What is this critical voltage which Coulomb dominate?
Look on this geometry.
Yeah.
You apply voltage between superconductor and normal electrode. Where is the electrical field? This electrical field directed almost along nanotube.
Blue and yellow electrodes. Between them, there will be.
No, okay. Let's take here insulator.
Where?
No. This is normal. This is normal, and this is all this.
What color you want insulator?
Huh?
What color you want to be insulator?
No, it doesn't matter. You want to draw. This is the range. Let's suppose you don't need this geometry. We have one electrode here and one electrode here. Forget about this region. Where is, of course, if you want electrical field, you can generate. If you don't want, you can choose a geometry when there is no any electrical field. That's it.
Okay.
I don't want to say about the value of this electric field because the voltage, bias voltage, is very, very small.
If I would just not appealing to geometry and say that electric field is voltage divided by some length, which is typical for this, what would be, who will be bigger, Josephson force or Coulomb force?
It depends on geometry, as you say.
No, I say in a worse geometry, when we have really electric field equal to voltage in your system divided by length of the device. It's a worse scenario for you. I mean, but I would like to see in a worse scenario when the voltage create electric field.
I think that this contribution will be much smaller than this influence of Josephson.
Contribution of what?
Of electrical field.
And what parameter will determine smallness?
No, something lambda divided by size of your system. So lambda is 1 angstrom, and the size of your mesoscopic system is.
This parameter should contain electric charge, of course.
No.
I mean, we're saying that a Coulomb force is negligible. If electric charge will go to infinity, it will be bigger, of course. Okay. So the criteria should contain electric charge. I mean, but doesn't matter.
Okay.
We will, okay, so that's, I have no questions, maybe.
Do we have any further questions from the audience? In case not, then let us thank our speaker again.
Thank you.
Thank you. Thank you, Roman.
So I suggest we take a short break, and whoever is interested in discussion, let's meet here after 5 minutes. Okay?
Yeah.
Bye.
Okay. Bye.
So we have joined again. What we should do?
No, we can stay here connected. You can just cancel the, remove the video and mute yourself. And after you come back, just unmute yourself.